here on Zoom. Is this, does this work?
Yes.
So thanks for coming to this seminar. We're going to hear from Jorge Martinez-Palomera, who's been working at NASA Ames with me and Jesse Dotson. Jorge has been working on Kepler data, archival Kepler data, and helping develop tools to extract background targets from this data. Jorge's going to tell you a little more about this and about how he's been able to get way more light curves out of the Kepler data.
Thank you. Well, yeah, as Christina said, I'm gonna tell you a little bit more. Just not just a little bit, like a lot about this. So in this work that I've been doing in collaboration with Christina and with Jesse Dotson down at Ames, we've been working with Kepler data. We've been extracting and creating these light curves for everything that all the sources are in the Kepler data, like in the backgrounds, also the targets. And well, this is the title. It's 400,000 new light curves from the Kepler background sources. We call this, you'll be hearing this word K-bonus. That's the name that we're giving to these data sets because it's like a bonus to Kepler. So yeah, let's start it. This is, okay, here's Jenny. I'm pretty sure you're very well versed, maybe even more than me in Kepler mission. You all participated there. But still, I'm gonna just give a small run through it. Kepler observed during almost 9 years. It was a space mission dedicated to search for exoplanets. During the first campaign, the first mission, it observed more than 200,000 targets, which cover the Kepler field covered like around 5 square degrees of the field. And it mainly targeted stars that are FJK type of stars, aiming to search for exoplanets using the transit method. Because there was a selection of the targets, of course, there is an observational bias of this data set. But anyways, also there was a second mission, K2. In combining these two missions, Kepler observed more than 500,000 targets, and it discovered more than 2,600 exoplanets that are confirmed. But not only exoplanets, studies were done with this data because it's so rich. There were done some supernovae, stellar activity, variables, etc. So Kepler really revolutionized the field of exoplanets. And there is even more there than the data products that the Kepler pipeline, the Kepler mission provided to the community. And that's where we're tapping into it now. So a quick summary of what the Kepler mission and the Kepler pipeline provided to the community. There were two main data products, right? The target pixel files, which were these small cutouts around the targets that were selected from an input catalog. These cutouts are usually like small, couple of like 5 by 5 pixels, up to like 12 by 12 pixels sometimes. There are others extended masks that were also saved during the observation quarters for different purposes. But these were like that was the main data product. And from there, the Kepler pipeline computed photometry using aperture photometry with these custom apertures that were selected around the targets, and then provided to the community with the light curve files, which is just a collection of different, like mainly a simple aperture photometry, but also a corrected version of those that are ready to do science, specifically focused into searching for exoplanets using the transit method. So this one like corrected for known systematics of the instrument. But the limitation of this is it only produce light curves for the targets, for the selected targets in the catalog. And this is a sample bias. So what we want to do, and we did, is actually extract everything that is in the pixel data. Here I'm showing an example of a collection of TPFs around typical channel 52 in this case, during quarter 5. We can see there are like several, the TPS come in like different shapes. Some of them contains like one single target with almost no contamination or zero contamination. And others contain like have more. Let me see if I can get my pointer. No. Others contains a couple, like a handful of background sources that contribute to the contamination of just a simple aperture photometry. The dots, the red dots are the targets in this plot, and the circles are Gaia sources that were queried down to magnitude 19. And those are we wanted to exploit and extract and get the light curves and deliver to the community. There are many, many more background targets, background sources that actual Kepler targets. And we can see that, and I will show you that in the next slide. But before that, I wanna like outline what is the main goal of this project. Now that we know a little bit more about the data. So the main goal is to extract the background, extract the light curves for the background sources, do different type of photometry, and then but also we want to provide to the community not only with the data but also with the tools to work with TPF like data, like the one that was provided by Kepler, and also test and perform the same routines that we did, perform PSF photometry, perform the corrections that we're doing in a quick way. And the steps to do that, to accomplish these goals, are we capitalize on the other catalogs that are available. One of them is Gaia. Gaia provides us with high accuracy astrometry of billions of sources. We use that into our method to perform then PSF, to create PSF model, perform PSF photometry, perform also aperture photometry, extract these light curves, correct them by the systematics that are introduced by the instrument, and also assess the data quality. And finally, and this will happen very soon, deliver these light curves to mass so then the community can access them. All right, so now let's go into what were the steps that we follow in our pipeline, in our analysis to extract these light curves. So first, I already mentioned that we use Gaia as an input catalog for the sources that we're going to extract. We query Gaia down to magnitude 19. There were like around 1 million of sources available around the targets, around the TPFs. Of course, we got to apply some cuts. There are some limitations. We will focus on sources that are in the linear regime of the sensor, brighter than 10 magnitudes in G, fainter than 19 magnitudes. We don't want sources that are like extremely blended within 1 arc second between each other, because it becomes really hard to then separate them. But we also allow for sources that are slightly outside the TPF, outside the pixel data, because we can still extract information from the wings of the PSF that can still be there in the pixel data. And after applying all this code, we got to that previous number that I mentioned of around 600,000 sources that we end up extracting during the 17 quarters that Kepler observed. 200,000 of them are the Kepler target, and the rest are background sources. And as I mentioned before, and I want to keep highlighting, is there's no target selection, because there's no target selection, there's no biases on this. I'm showing here on that distribution plot the apparent magnitude of the backgrounds targets in green. In orange are the Kepler, and in blue is the addition of both. And these other two figures here that shows the density of sources around the Kepler field. The top panel is showing the Kepler targets, and the bottom panel is showing the background sources with a greater density of sources, especially when we go closer to the galactic plane. So this is just again to highlight just the volume of how many sources we are extracting. Now going into the actually into the tools that we use. We started developing with Christina this Python model, which is called PSF machine, because it does PSF photometry. And it has different user interface that allow us to interact with TPF data, with full frame images, with super stamps, also from Kepler, different stuff. And what it does, it implements a method that we call linearized field photometry that was introduced in a paper by Christina last year. What it basically does, it fixes the target, the location of the sources by using Gaia, for example, by using an input catalog. And then by means of fitting a linear model, it computes a PSF model and then extract the photometry. And because it is all some mathematical tricks, it ends up being linear algebra. It happens very fast. We can extract in around a minute or 2 minutes, a batch of 200 TPFs with around 600 sources in them, which is pretty fast for a PSF method. You can go to our GitHub, use the package. It works very well with Kepler data. It works fairly well with K2 data. It will do it better in the future. And it will work also with tests. But ideally, I mean, the method can be extrapolated to any kind of data where you have flux information, coordinates, and an input catalog. Let's move on. So in our pipeline, we run this by batches of TPFs. Here I'm showing a collection of, I think, 250 TPFs in one of the channels. Again, I'm highlighting the sources with red circles. And what we want to do, again, query Gaia to get our targets, and then fit different models that will take us to the final goal of extracting the light curves. We will fit a background model. We will fit a PSF model, or a mean PSF model, as I'm going to call it later, and then a perturbed PSF model that will account for systematics in the instrument, in the data. We are using all the TPFs, not only like the standard ones that were used for science, but also there are some like extended background aperture masks that Kepler saved, that were 36 by 9 pixels across, with no target selection there. There is an example on the right-hand side of the plot there, of the figure, of this like big patch of pixel data. The Kepler actually never, sorry, the pipeline never extracted light curves from there. They were meant to be used for estimate the background ratio of eclipsing binaries, which is a common contaminant for false positive in exoplanet searches via transit method. And we actually, last year, we ran like a prototype model where we run that data, but only doing aperture photometry. We put out those light curves at the Mass Archive last year. We found an exoplanet candidate in that data, which is pretty cool. But now we are doing the full thing. We are doing PSF photometry and aperture photometry and everything. Moving on, the first thing was model the background. We want to subtract the background signal. There is a very distinctive signal in the Kepler data that is called rolling band. That is this time-dependent background signal that moves almost vertically in some of the sensors. And our model, we modeled that in a way that it is computationally efficient, but it also takes care of this signal. Because the signal is mostly row dependent and time dependent also. Our model is in functioning row and time, like pixel row position and time. And in these figures here, I'm showing in the top figures, the left panel that is the data for the background sources, sorry, for the background pixels as a function of time, each row. So it's like a time series of each row, which was averaged in the columns. And then the model in the middle panel. As you can see there is like this signal that is coming from the top row and moving down as time passes. That's the rolling band signal, and we capture that with our flexible model. This is good. We can create a very good background model, but the problem is sometimes the background pixels in the TPFs are very sparse and are just a handful of them where we are looking at very crowded regions. So we need to account for that, and to do that, we augmented our data set, our background pixels, by using the engineering data that was observed. This is like a almost homogeneous distribution of pixels around across the CCD that only say background pixels and were used for the Kepler pipeline to estimate the background. And we actually include those to the background pixels from the TPFs to augment this and fit a more robust background model. This should be playing. This should be a movie, actually. Yeah, there we go. So in the lower figure in the movie, the left panel actually shows all the background pixels that we use, combining the ones that are coming from the TPFs and the ones that are coming from the engineering data. And on the right-hand side, we can see the model background evaluated in the TPF data. And there is like a slow transition. It's like a general trend of the background going from brighter values to lower values with the rolling band signal in the row axis. So we have our background model, we subtract that, and now we move into fitting the PSF model. I previously mentioned that our pipeline, our method work not only on TPFs, but we can also work with full frame images from Kepler. And we actually take advantage of that, because if we compare a full frame image with all the TPFs in a channel, there's much more data in the full frame image, of course. There are more pixels. So we can create a better, smoother, robust PSF model. That's what we are doing here. A classic, I mean, on average, a full frame image from Kepler contains around 10,000 sources from Gaia down to brighter than magnitude 19. And using those 10,000 sources, there are around 100,000 pixels with flux information coming from those sources that are usable to create a PSF model. Comparing those numbers to just a couple hundred of TPFs, this is like 10 times bigger. And you can see here, this is a render of one of the FFIs with all the Gaia sources. And in this case, it's very crowded. There is even one of the clusters on the top left corner. So we use that data to feed our PSF. There are a couple of assumptions to feed our PSF. We do it on polar coordinates because polar coordinates are nice. They have symmetry. The PSF broadly have this circular symmetry also. We do it also on logarithmic space, and we feed a model with components that are B-splines. We feed a linear model, and this is what we get. In the top row, I'm showing the data, and in the bottom row, I'm showing the model in polar coordinates on the right-hand side and Cartesian in the left side. And each point in this plot corresponds to a pixel that is contributing flux to its closest source. So that's how we build this model. We can see for this example, this is channel 37. The shape of the PSF is very smooth, regular, with some like distinctive structure in the wings. And this is the PSF model that then we will apply in the TPF data, as I'll show later. We compute this for all the channels and all the quarters that are available. This wall image shows all the PSF models for quarter 5. That's why the model number 2 is missing. And we can see they have, I mean, in the center, they have fairly circular shapes, but as we move to the edges, the shape of the PSF becomes a little bit more distorted, elongated, with distinct structures in the wings of the PSF, as it was expected for the instrument. This is what we call the mean PSF, and with mean I mean it is the mean model that we fit for our full quarter. And with that, we can create like a mean photometry light curve. We evaluate that PSF in the grid of pixel data from the TPFs. This figure is showing kind of similar stuff that we saw in the two slides before, but now evaluating that very smooth, dense model in the data coming from the TPFs, from 200 TPFs. I mean, and it's easy to see that the data points near, for example, the center of the PSF are very sparse because less number of sources, but also the scale of the pixel, right? We can like avoid that, or not avoid, but work around that by just having more sources, more data point, as we did on the FFI. And we fit this model to the TPF data to extract our photometry. But we know that the PSF slightly changed within the quarter because multiple factors, because there's velocity aberration effect, because data downlink, and then after data downlink, the instrument had to adjust focus, because attitude corrections from the thrusting wheels, etc. All this slightly change either in size of this PSF, but also a little bit on position. We can model that by introducing a perturbation on our mean model. And we did that by using a couple of 8 different components. We have components coming from a third-degree polynomial in time that mostly account for the smooth movement in the scene. And also we use the first 4 CBBs, the co-trending basis vectors from the Kepler pipeline that account for the non-systematics of the instrument, like the focus adjustment, for example. In the top figure, I'm showing actually an example of those 4 CBBs. We actually use a smooth version of them to avoid introducing high frequency noise. And in the lower plot, this is a movie of our perturbed model. The data points in the figures are the same in the same locations that we saw before for the PSF model, but now the colors maps to the perturbation around the mean value, if it's higher or lower at that cadence. And you can see how this smoothly transition because of the drift and the movement of the instrument. Ideally, we would like to do this for every cadence and have a perturbed model for every cadence, but that is computationally very expensive because we have almost 4,500 cadences. These matrices are big. It will take a few hours to do it, and also some quite memory. But we just bin down the data. That follows the assumption that in Kepler, at least, the movement of the scene is slow, is smooth overall. That doesn't quite hold actually for Kepler, for K2, for example. So there are some like tweaks that we can do then in the future for that. But yeah, it works pretty well. That's our perturb model. We also sometimes call it time model. I mentioned before that we also do aperture photometry because we have these very nice PSF shape models. We can feed it to the pixel grid and get our model of a source, and then find an aperture that nicely fit the shape of the source, right? The shape of the PSF. And we can also compute different metrics to balance this aperture. Inspired by what the Kepler pipeline did, we compute two different metrics. Flux ratio, which will be the amount of flux of the aperture over the total flux of the source, and crowd sub, which will be the flux coming from the target over the total flux on the aperture that will account for the contribution of contaminants. And we can tune that. In this figure, those stamps show the first column of images shows the data, and the second is the PSF model of our evaluated on the source. And those red crosses show the aperture that got selected for that particular source. And the graphs show these two metrics that I mentioned before as a function of the parameter that controls the size of the aperture. And we can optimize that, or like, for example, favor completeness or favor contamination or less contamination, etc. We actually try to have less contamination. That will mean a crowd sub metric close to 1. That is what's signaling the vertical line in the figure. And we have some examples of isolated sources, like the second row, where that source is like, it have almost zero contamination from neighbors. We have an extreme case of a highly contaminated source in the third row. That in the case we want to optimize for crowd sub metric, we end up having a small aperture of 1 pixel. And other two, like the one in the top and the one in the bottom, that are in between. So we can do that. We can create aperture photometry too. So this takes us to the 3 different flavors of light curve that we have. We have aperture photometry, mean PSF photometry, and a corrected version of that PSF. In this figure, I'm showing a very good examples of this type of light curves. The top panels show the TPF data, the TPF image with the aperture highlighted. That's the aperture coming from the Kepler pipeline. And the light curves are the light curves corresponding to the sources in that TPF data that are marked with a red with white circles. The 2 panels on the left show the light curve in red, our SIP, our aperture light curve, in blue, the mean PSF, and in black, the corrected PSF, which most of the time is flatter than the mean PSF, because the mean PSF contains a lot of the instrument signal. That's the one, the black one is the one that we encouraged for the users to use. We also include multiple metrics that are related to the aperture, as I mentioned before, that are related, for example, to the amount of PSF flux that is in actually in the data. Like in the example of the right hand side, there are 4 sources that are outside the pixel data, but we can still fit and extract PSF photometry from them. But that PSF is not complete, so it's not full in the data, so we have a metric to account for that. Now moving into the overall results of our data set. I I mentioned before, we have around 600,000 sources in our catalog. 400,000 of those are more than that number are background sources. And here I'm showing the color magnitude diagrams for those subsamples. First, we have the Kepler targets. In the middle, we have there the K bonus, which are our background sources only. In case you're curious, this is the like the over/under density ratio between the background and the target, just to see like where we have more or less than compared to the Kepler sample. And on the top, we have, I mean, everything, the whole catalog. There are some interesting data sets or subsamples of data could be interesting for some of you. 40 new white dwarf that we extracted. On a quick search, we didn't find anything interesting, which is kind of sad, but maybe other people can find something very interesting there. There are almost 20,000 new M dwarfs, 5,000 of them within 1 kiloparsec. Those are interesting too. And we will provide this in like not only as a like query based as mass does, but also as bundles. Like let's say if you are interested only in the M dwarf, you can grab those very easily and do your science. More examples of light curves. These are preliminary in the sense that we still need to do some like cleaning of some light curves to ensure that the data products that we're releasing are reliable and users can trust them. But these are very cool examples of false positive KOIs. Because we're doing PSF photometry, we can easily deblend contaminated sources. These are two examples. The bottom figures are showing the TPF with red dots are the sources. The one in the center is usually the target. And the top light curves, the blue light curve is our light curve for the target, for the KOI. Maybe it'll be hard to see, but behind that there is a gray light curve or a black light curve that is actually the one that was extracted from Kepler pipeline. Because it's a false, it is a candidate that was labeled as a false positive. It shows a transit signal that our light curve doesn't show because we were able to deblend this. And the other rows of light curves, we see the neighbors. So in the first case, we have a neighbor that is, if I can see right, is 1.3 arc seconds away. It's within the same, almost within the same pixel, but is almost 3 magnitudes fainter, and we can deblend them very easily. So we know who to blame here, which is contaminating the target light curve. The second case is another good example. There are two main neighbors around this target. One of them, which is eclipsing binary 1 arc second from the target, which is the one actually the one having the transits. And there is a third target that actually doesn't play any role, but just showing in there for completeness. There are many examples of it. We can like go hours and hours through the whole list of KOIs, finding where the signal is coming from. There is another good example where we are really good at separating blended sources and finding the real variable. Yeah, another pretty cool example. All right, so I'm gonna go through this now. I also revisited some of the confirmed exoplanets. I think I did 1,500 of them. I only use light curves for this. Is very preliminary. I only use light curves from quarter 5, and I recompute we recompute the BLS to find difference in the depth, in the transit depth, and compare it from the Kepler light curve and our light curve. So this figure is showing that in the x-axis we have the transit depth coming from the catalog light curve, and in the y-axis our light curve. The relation is pretty good. It's almost, I mean, the density of the source is like right on the identity. Of course, we have noise because there are noise. Sometimes we have noisier light curves that Kepler. Sometimes we don't. It's the other way around. but also some of those data points outside the identity are because there was no clear transit signal in that particular quarter. It could be in another, so this figure should improve as we include the whole data set. And those Likers on the left, again, show some of these examples. In blue is our Liker, in black is the Kepler. It's great to see that we can recover Kepler Likers with a similar signal to noise ratio with a similar transit depth. Sometimes we even do better. Sometimes we don't, depends. Finally, we will deliver this data set in a ready-to-use way. And with that means you're all familiarized. Kepler did it in a per quarter basis because as they were getting the data, they were releasing the data products. We're going to release everything. This is an example of how our Likers will look like. We will have the stitch version of all the quarters of all the data that is available, but also the per quarter Liker in case user want to use that. Here we have three main flavors of the Likers. One will be just the corrected PSF photometry, which is the one that I'm showing in the top. These are like a variable, and a variable and an eclipsing binary. We will also provide the same thing for SAP for the aperture photometry. We will not do it for the mean PSF photometry because the corrected version is better. But also we are providing with a flattened version of the PSF photometry, which is the one that you will like to use if you're doing exoplanet search. That will remove the stellar activity, the stellar variability, and hopefully preserve the transit. So that's the one you want to aim if you're looking to do that. If you're looking to do stellar activity or variability or like long-term variability stuff, the corrected PSF version will be the one you want to use. So to wrap up, I want to highlight some things. We're releasing, again, more than 400,000 Likers of new sources, 200,000 of revisiting the Kepler targets, doing PSF photometry, doing aperture photometry. We're matching what the similar Kepler format, so then it's in like an easy transition to use this data set, and it will be available at mass very soon. We also have the PSF machine Python model that you can also use to analyze your, extract Likers of your favorite sources in the Kepler data. In the K2, we are still working to get in there. There are some like tricky things that we need to do to work with that. And also it will be available for test data. So I want to leave you with this. There will be many opportunities to find new candidates in this data set. There are opportunities to confirm or rule out the false positive KOIs. There's also opportunities to study stellar activity because we have 400,000 Likers there, new Likers there, and many other variability studies that you can come up. So yeah, that's me. Thank you.
Yes, so do you have any questions for our speaker?
Yeah, this is awesome. This is cool. I was wondering if you looked at the Likers of any of the clusters.
Yeah, we actually did. So I'm just gonna repeat the question for the guys that are in the Zoom, asking for if we did this analysis for the cluster data. We did it. We did like a prototype over there with the cluster from K2. We found some good results overall. We actually had to do some tricks there because at least for K2, the gyro motion of the spacecraft is like all jagged up, right? We actually have the option. We have a dedicated model in PSF machine to work with K2 data and to do PSF photometry at each cadence, to compute a PSF model at each cadence. Of course, it takes more time. It takes like a couple of hours to do it for one of the for a portion of the cluster, but it gives you reliable results even without even using the mean PSF method and the corrected version of that one, computing the perturbation and beams. And if you provide the right basis for like your right regressor basis, like for example, the position corrections for the centroids, you can get very good detrended sources that are on par with others, with other teams that also have extracted for the clusters. And in the fainter side, they tend to be slightly better. We are not releasing them really yet because we still need to revisit that and do a better. We think we can do maybe a better job, improve on some stuff, but it's promising. Yeah. Yeah. Mhm. Yeah. The good thing is the current version of PSF machine has the tools to do that. Has the tools to do a PSF model at each cadence or in the beam data. You can provide the different regressor bases, whatever. And you can easily load the data actually, which sometimes comes in different formats. Yeah.
Awesome. Just for the group online, feel free to raise your hand or post any questions in chat if you have any. I had one for you.
Yeah.
That was a great talk. Really awesome work that you're doing. At the very end, you kind of teased the idea of working with test data. Like, I was just wondering if you could kind of expand upon that. Like, what challenges do you foresee, or can this move pretty easily into working with that?
It moves pretty easily. We have done some prototyping. It's actually the infrastructure in PSF machine is already there to use it with test data. It's just a matter of like find the right parameters, the model parameters that work with different pixel scale, different levels of contamination, stuff like that. But yeah, if you dedicate some time in it could be very straightforward.
Anyone else have any questions?
Mm-hmm.
Here for the next week. So any of us have already one of that sort of stuff
Yeah.
on their work. If anyone wants to talk about how to do similar things for their candidates at a grad course, usually say around W16D, and we're so happy to talk to anybody with any data about how to do this. So please reach out.
Yeah. All right. Thank you all.
Yes, well, let's thank our speaker again. Thank you so much, guys. That's awesome talk. All right, and we will see everyone next Friday for another hybrid talk. Thank you all online for coming out today.